This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
For Software Engineering Radio, this is Stefan Tilkoff. Today I'm joined by Kyle Kingsbury, better known by his Twitter handle Afear, to talk about database consistency. Kyle has become quite famous in the community because of his tendency to break databases, that is, use rigorous testing to show how they deal with various error scenarios. I've been a long-time follower of Kyle's posts and talks, and I'm sure you'll be as fascinated as I am by his insights into the theory and practice of databases handling failure, or, unfortunately more often, failing to do so to varying degrees. Kyle, why don't you start us off by introducing yourself and tell us a little bit about yourself?
Well, my name is Kyle. I'm a back-end engineer by trade, and I work right now at a company called Stripe, where I'm doing database safety analysis, trying to understand whether or not distributed systems, caches, databases, queues, that sort of thing, whether or not they live up to the guarantees that we expect from them.
Okay, so for those of our listeners who haven't really, been exposed to those kinds of problems, can you talk a little bit about what issues might arise when people use technologies like that?
Sure thing. We see consistency problems all the time. For example, you might go to Twitter and read some direct messages, and then go from the website to your phone, and you'd notice the same direct messages are shown as unread. That's a synchronization problem, a consistency problem, where different computers, different clients have different ideas about the state of the system. And this goes much deeper. You can get into errors with bank accounts. For example, there was a famous Bitcoin exchange that lost a lot of money because it did not correctly debit and credit accounts in a transaction. Facebook, for example, has all sorts of interesting out-of-order issues with display. These are problems that arise sometimes because there's simply no good way to do them at scale, and sometimes just because we didn't understand what the necessary safety primitives were.
So is this something that only companies that run really, really big data centers are exposed to? Do I have to be running something like Facebook or Twitter to run into those kinds of problems?
I don't think so. But it's tricky to give us good data about it because most people don't instrument their consistency. They don't measure whether or not the system is actually safe. So one of the things I'm trying to answer is how likely is it that you might see real-world impact during certain common failure modes?
Mm-hmm. So one of the things that I often run into is that people who use traditional relational databases, the Oracles and DB2s and MySQLs and Postgres, whatever, those kinds of things, believe that they don't have to worry about those things. Are they right?
Yeah, it depends. Like, there are certainly consistency issues in relational databases as well. There was a paper published recently, actually, on a Postgres error where its serializable isolation level failed to be serializable in a sort of surprising way. And so I think you'll find these safety issues affect people both at the level of bugs and just because understanding the weaker ANSI SQL isolation levels is a little bit tricky. The spec is not entirely clear about what should and shouldn't happen.
Can you talk us a bit through those isolation levels? Not necessarily all of them, but give us an idea about what is specified there.
Sure thing. So, as I understand it, as relational databases are sort of coming to their own, different database companies realized that it was impossible to provide complete, nice global orders for events in the system. You want all your transactions to look like they take place sequentially one after the other. But actually doing that is relatively expensive. And so maybe there are shortcuts. Maybe you could avoid taking out a complete lock and allow two transactions that don't touch the same data to complete at the same time. When you do that, there are different trade-offs you can make regarding how long you acquire the locks for, whether you lock for reads or writes, if you do multi-version concurrency control. You can get different sort of what we call anomalies. They're behavior patterns, orders in which transactions can execute that look maybe a little bit dodgy. In some cases, they're okay. but in some cases they're not. For example, we get a problem called phantoms, where you might write a new record into a data set, and at the same time you make a query against a table, and that query should have seen the new record, but does not because its predicate didn't yet match for whatever reason. So maybe access to the same row in the table is synchronized correctly, but that row might not appear in a query that should have seen it. It's a sort of subtle, tricky thing to reason about. So what happened was the different database manufacturers were starting to standardize, and nobody wants to be left out. So we have this standard ANSI SQL that codifies different levels of safety, and those levels sort of correspond to whatever trade-offs the databases might have made historically, so that everybody could say they slotted in somewhere. So in practice, you'll get a wide variety of interpretations of those anomalies, and then different levels of actual conformance to the spec.
One thing that I find interesting is that you can actually specify some of those or configure them, right? You can make a decision of what kind of isolation level you want. So this idea is nothing new. It's been there for a long, long time that people can have to make trade-offs regarding consistency levels, right?
Exactly. Yeah. So you can choose to jack up the isolation level to serializable for every transaction, but this is somewhat slow, and so a lot of people will start off at read committed or even back off to read uncommitted, depending on what their application needs. That's the ideal case, but some people, will just turn it down to read uncommitted or leave it at the defaults because it's faster without understanding the implications and without fully reasoning through the transactions. I think it's sort of an open research problem right now of we're not sure which transactions, which patterns of access in the database require which isolation levels to be safe.
Mm-hmm. So how is this related to the famous CAP theorem, and can you maybe explain that to us a bit?
So there's two things. There's a CAP theorem, which is a formal proof by Gilbert and Lynch, and that tells us that of consistency, which they mean linearizability, availability, which they mean total availability, that is every request to a non-failed node, a non-crashed node, must succeed, and of partition tolerance, that's the P in CAP, you can only have 2 out of 3. Now, that actually derives from a sort of conjecture or informal claim made by Barrett Brewer that of consistency, availability, and partition tolerance, there's some trade-off, and you can really only get 2 out of 3. Mm-hmm. So when people talk about CAP in a modern context, I think they're typically referring to the proof, which has very strict definitions about what availability and consistency mean. But that doesn't mean that by relaxing consistency, you necessarily get availability. There turns out to be other proofs that exclude different classes of operations, different consistency classes from being fully available as well. So CAP is a very particular example of this sort of larger class of problems of consistency. A consistency model is a set of allowed histories, allowed behaviors that a database could go through. So if you were to take all of the different operations you do, like reading a value and writing it into some other table, or incrementing a number, or setting 3 fields at once on a given record, those are all sort of transactions. If you take all the transactions in a system, in practice, the different transactions are applied somewhat concurrently. Maybe somebody's writing data and somebody's reading data at the same time. What you want is for the operations to take place in some kind of order. So maybe part of a transaction takes place first, then another transaction sneaks in and does a little bit of work, and another transaction comes in, does a little bit of work, the first transaction comes in and finishes. There's lots of different ways those events can be ordered, and the consistency model is the class of allowed orderings of those events. So CAP tells us about a very particular consistency model, just like ANSI SQL tells us about certain allowed models, like read uncommitted, read committed. They prohibit certain classes of orders. They prohibit you, for example, from reading the result of another transaction's write until your transaction is committed. Or you might get snapshot isolation, where all of your operations are supposed to take place on some atomic snapshot of the world that occurs at some logical time just before your commit. Those consistency classes can only be achieved in certain availability models. And there's different theorems that tell us which classes are achievable in which availability settings. CAP tells us that one of the strongest classes of consistency, the one which allows the least number of reorderings, well, not the least, but a very small number. It's still infinite. It's complicated. CAP tells us about linearizability, which is this very strict ordering, and it says that linearizable systems cannot be made to be fully available. If you build a linearizable system and it experiences a network partition, a communication failure between nodes, it's possible for transactions to stall forever or for transactions to be incomplete. You either have to deadlock or give up on certain operations.
I think everybody can imagine what consistency means, sort of. You mentioned linearizability, and the system goes from one consistent state to another, and you have this feeling that there's no you don't get a dirty read of some kind. You don't get half committed things, and you don't miss anything that has been written or has been committed. I think everybody can imagine what availability is about, but I always feel that people struggle with this idea of partition tolerance. What is it? Why use a term like that? What does it actually mean?
I think of the three, partition tolerance is the easiest to understand.
Oh, that's interesting. How so?
All it means is that the system should be resilient or should continue to function in the event that messages are not delivered.
Mm-hmm. Okay.
And we see this happen in production networks all the time. Microsoft ran a really interesting paper in SIGCOMM a couple of years ago where they measured their database packet loss over several years. And they have a lot of machines and a lot of routers, and they actually gave pretty good quantitative evidence about the frequency and severity of partitions. It turns out to be far more common than you would expect, even with good change control, even with good hardware.
Mm-hmm. Okay, so a partition can occur for any number of reasons. It doesn't matter whether it's actually the network being down or some other problem along the way. It's for some reason the message doesn't arrive at the node it was supposed to arrive at. Is that what it's about?
Yeah, exactly. So it could be a delay, right? Because delays and drops are sort of indistinguishable from one another on a short timescale. If I'm allowed to arbitrarily delay a message, I can always outweight you as a software system. Because at some point you're going to say, well, all right, I give up. It's not going to happen. So you can get garbage collection pauses. For example, when a runtime stops execution of the program to clean up some memory, no messages will flow in or out. So that introduces a delay, and that can look like a network partition. The operating system, if a disk scheduler goes south, a lot of times that will stall I/O operations. And so if you're stuck waiting for the kernel to do some I/O, your program might not be running anymore. And so you again have this sort of delay. Network partitions can happen from the actual network. If you have a cable that gets killed by a backhoe or unplugged, you'll get into logical software errors where a race condition occurs and some messages never get sent. There's all sorts of different ways this can happen. Okay,
so if as you said, I can pick any two from those three properties. Can you walk us through the three options? Do they all actually exist, and what kind of what's the result if I have a CA, a CP, or an AP system?
So there's been some debate about what 2 out of 3 really means. Well, the paper is very explicit. It says if you ever have a partition, you must choose either AP or CP. And experimentally, it looks like networks do experience partitions on a relatively frequent timescale. Given the partitions are going to happen, I think we should make AP or CP trade-offs.
Okay, so there is no CA because there is no system that doesn't run into partitions anytime.
There are maybe systems that do not run into partitions anytime. If you have a synchronous network and you're very diligent about maintaining it, you're okay. However, any system which is CP can also be totally available if the network doesn't partition. So you might as well shoot for AP or CP and simply, in the common case when the network is working, do everything correctly.
Okay.
So you can have both as long as the network is running, and then you degrade to one or the other. It's sort of like asking, if something bad happens to your network, which are you going to preserve?
Okay, so let's talk about those two, AP and CP. What kinds of trade-off am I making if I choose one of those two?
So AP databases offer you availability first and foremost, and that means total availability. That you can make a request to any node. You can make a write, you can make a read, you could make an update, a complicated query, a compared set. Whatever you want to do against any node is fine. This makes them really good candidates for highly available systems in a single data center, but it also makes them good candidates for distributed systems that are geographically replicated, because you can write independently in any given data center and with low latency immediately return a result. So that's a wonderful property, right? Everybody wants that.
For people who consider that, does an AP system give up consistency completely, or what does it actually mean to have an AP system then?
So A, in the sense of the cap theorem, means total availability. And there's a whole bunch of different proofs to tell you what the sort of maximal consistency models are you can get. There's actually infinitely many, but the common ones are going to be writes follow reads. So you guarantee that if you do a read of a read of a given value, that your write is logically successive to that. You can get monotonic reads, where if you read two things in a row on the same session, they're going to happen sequentially in the sort of logical order of the system. Monotonic writes, where a write will follow a write. You can get read committed, monatomic atomic view, and also PCI, which I do not remember what the acronym stands for. But all those things are totally available, so you can have these guarantees of what your system will do. They're so consistent. It's just that they don't exclude all classes of operation.
I see. So having an AP system just means that I don't have 100% consistency. It doesn't mean that I don't give up consistency completely. I make some trade-offs regarding consistency to achieve this 100% availability. Is that a good way to phrase it? Okay.
Right, exactly. And it's not like it's a fractional consistency. It's that it is 100% consistent with respect to that consistency model.
I see.
So your system is completely safe if it obeys certain rules. For example, if you use CRDTs, convergent replicated data types, it's okay to do updates anywhere you like, and they'll eventually converge on some value. If that's your data model, a system like Riak or Cassandra, where it's AP and it doesn't offer you any sort of guarantees about when you're going to read data, that is safe. But you can't do all things with it. If you want to do a counter, for example, in Riak, you have to deal with the fact that you might write a value and somebody else might not see it for quite a while until that data is replicated over. So you have to be okay with allowing more histories, wider windows of concurrency in the system.
Okay, you already mentioned two examples of AP systems. Do you have a bunch more that you could just briefly mention? Not explain. I think we'll get to that. Just tell us what are typical AP systems.
Yeah, so Riak and Cassandra are both Dynamo clones, which comes out of a paper called Dynamo from Amazon. There's also Voldemort and a few others. The sort of lesser, a lot of people don't think about them this way, but I think if you have like a cluster of memcache machines or a cluster of Redis machines that are sort of independent and you run your own sharding layer on top of them, in a lot of cases that is sort of analogous to an AP system. Now, it depends. CP is also sort of rare because in order to be truly CP, you need to be linearizable, and relatively few databases are.
So let's talk a bit about CP then. That will be another trade-off. I give up some availability. I don't have an unavailable system. I have a system that makes a higher priority of consistency than of availability, right? So I restrict this property of having, as you mentioned, any node be able to accept a write or read. So what is a typical kind of system that I get if I shoot for CP as opposed to AP?
So, yeah, exactly. You can still be highly available, but you cannot be totally available. So in a CP system, the trade-off you'll typically see is majority quorums, where you must have a majority of nodes reachable and connected in order to make progress. If you're on the sort of minority island, or if you're on a single node that's isolated, you've given up the ability to do some or all operations. You might be able to get a reduced set of operations, like maybe I can read data, but it's not guaranteed to be recent anymore. So the really common ones here are going to be Zookeeper, etcd, even WANDisco has a Paxos implementation inside of it. I think FoundationDB is claiming to be relatively strong, although I don't know if they promise full strong serializability. And there's a broader class, so linearizability makes certain guarantees about the wall clock time. If I write a value to a linearizable database, and then it comes back and says, okay, your write is complete, I am guaranteed that anybody else that makes a request after that in wall clock time will see that write. But there are other sort of strong consistency models which are also not totally available. So sequential consistency, which guarantees you have a total order of all events, and that every process sees the same ordering. That is not totally available. Serializability and strong serializability, which simply enforces there must be a total order, and we're not sure what it is. Those are both prohibited as well. You can't even have repeatable read or snapshot isolation or cursor stability, which are the kind of strong ones on the SQL side of things. Those ones cannot be totally available either. So if you were to build a cluster of MySQL nodes, like what is it, Percona, to something like this. If you have like an Oracle cluster or whatever, there are theoretical upper bounds on how available that cluster can be in order to meet the guarantees of cursor stability, repeatable read, so on.
Very nice. So after all this theory, maybe let's go to some practical things, right? So one of the things that I found really fascinating is that you did not only write a bunch of smart blog posts, you did, but you did not only write them, based on academic theory. You actually tested systems, and the system that you developed for that, or the tool that you developed, is called Jepsen. Can you talk a bit about what that is and how you ended up building it?
Yeah, so none of the things that I've said are particularly novel, right? This is all, I think, relatively well understood research in the academic field, dating back to really the 80s. However, I think if you're a practitioner right now, somebody who's going out and building a backend for a website or something, it's really not common for somebody in that position to have the time or the interest or the training to go and read academic papers. It's not an easy thing to absorb. Even for me, like, it takes me a full week to read a paper. What do I read? Where do I start? There's no good books. And because consistency is not something that's going to bite me right now, if I'm under a time crunch, which I think pretty much all engineers are, I'm just going to prioritize building more features and getting stuff out the door. And if people start to complain, I'll go look at safety and consistency. So we're in a world where engineers are not cognizant of the literature and don't believe that the literature describes failure modes that could actually happen to their system. And it's unclear, because we're not measuring our systems, whether or not that's a real problem, right? Like, okay, Redis Sentinel seems to be really unsafe, and these sort of academic wankers say it's unsafe, but is it really? Like, it seems fine to me. I've added numbers, and I've done reads, and they seem to be all right. So I wanted to build an experimental harness to actually measure whether or not these theorems had sort of measurable real-world consequences.
So how did you go about that? I mean, you would have to set up all of those systems and derive some abstract thing. What was the actual process that took you there?
So Tom Santero and Mark Phillips asked me to give a talk at Recon, Distributed Systems Conference in New York in 2013. And I scrambled to figure out what to do. I knew I wanted to talk about consistency, but wasn't sure how to really do this verification thing. So the software that I wrote was very simple. It just said, let's add a bunch of numbers to a set, and then we'll read the set, and if all the numbers we inserted are there, it's good.
That sounds easy.
So this doesn't require order. You can reorder stuff in between, but it's something that you can implement on most databases and get some understanding of the safety properties.
Okay. So how did you build that? What database did you pick, and how did you end up building this kind of thing?
Originally, I wanted to do React, because there was some mailing list discussion about the last right wins behavior. So I did React. There was something from anti-res that I thought was a little dodgy in Sentinel, so I was like, all right, let's take a look at Redis too. I wanted to do MongoDB because that's sort of a very common and popular database that a lot of people are trying out, but has historically, its public perception has not always been so positive as far as safety goes. And then Postgres, which has this reputation of being, completely safe and ironclad, and in fact, they're doing very good engineering work, but there are some subtleties that you might not think about. So I took those 4 databases and wrote harnesses for each one that hooked them up to this little set machine, right? So it's going to add numbers, and then do a final read, and we'll check to see how many were dropped and how many were present in the final set that we thought might have failed, and it has all these statistics and computes. And then I started out by writing a proxy, actually, to everybody's database would talk to my proxy software, and it would route the connections for you and drop them. That turned out not to work very well. And so what I had to back off to was running each one in a separate VM, and that turned out to be slow, so I ran them in LSC instances, and that kind of worked. And so I wound up with a sort of horrible mishmash of shell scripts and Ruby and Clojure that would cut off things with IV tables and induce slowness and measure the results.
Okay, so essentially the software is out there, and anybody could test your results and verify your results, right? And just have it set up a cluster of whatever database, with all the databases that you've taken a look at so far. And how many databases did you take a look at by now?
We did 4 in the first round, I think 3 in the second, and 3 in the third. So I guess we're up to 10 now, maybe 11. I'm almost lost track. And there's been some sort of side work that was more theoretical, looking at modeling. The latest round I'm working on right now, it's probably going to be another 3 databases, and I'm hoping that will show up in some talks this spring.
So if you had to categorize those results, was it like 90% just a pass with flying colors, everything was great, and there was just a very, very few that broke, or was it all were bad, or what was the general kind of the type of result that you got from those tests?
It's always surprising. I think every time you go and measure something, you discover something new and fascinating about a system that you trusted, and oftentimes you discover more questions you never thought to ask. This is what I love about experimentalism. Like you get to just throw random stuff at a machine, and unusual behaviors occur. In MongoDB, for example, I knew that the defaults weren't safe. They just wrote to a socket and did not check to see if it actually went anywhere. They just assumed your write was safe. Like, that's obviously wrong. And you could show that without too much trouble. But they were in the process of migrating to a stronger one where you would verify that at least one machine had accepted it. And I also knew that wasn't safe and was able to demonstrate that. What I didn't realize was that even the majority level where it confirms act from the majority of nodes in the cluster, even that is unsafe. And I actually discovered this bug and worked with the Mongo people to fix it, where if the network failed, it would check off the OK box and send the request back to the client just to get it out of its hair. It's like, all right, I don't know what to do with this thing. Check, OK, you're done, send it back. And so that was a sort of unexpected and delightful behavior. And in Riak, nothing was that surprising. We knew last write wins was bad. The documentation still last write wins is bad, but it was still the default, because Basho has a bunch of customers who, for various historical reasons, expected and wanted this behavior. And having an actual blog post I could point to that says, look, you're going to drop 70% of your data if you use this thing in this way, was sort of a wake-up call.
Okay. So maybe we can spend just, I don't know, one minute at most with each of them. Just remember what you thought of your results and what your general impression was, and we can go through all of them. So I have the list before me, and I will of course put the list of the blog posts in the show notes. So let's start with Postgres.
So the Postgres finding is it's a subtle and not terrifically scary phenomenon. It just leads to false negatives. The reason is that Postgres sort of does this two-phase commit thing where I'm going to tell Postgres, okay, commit my transaction. Postgres goes and checks if it's okay commit, and then sends back a response saying, okay, you're done, and then we've both agreed that the transaction is complete. If that final message is lost, 2PC is not partition tolerant. It will just stall forever. And so what the client eventually does is time out and said, okay, your transaction failed, when in fact the transaction could have succeeded. Mm-hmm. And I just managed to show that experimentally. You get into situations where you say, hey, I did not write the number 2. The number 2 failed a transaction. But in fact, the number 2 would appear in the final read because Postgres had committed it, but the response had gotten lost.
Okay. Redis.
Redis was a complete disaster. The Sentinel protocol had numerous race conditions and all sorts of issues with safety. It would enter permanent split brain. You would get independent chunks of the cluster that evolved separately, and I think it never actually recovered. I think it just kept going in split brain forever. Yeah, unmitigated disaster. It's better now, somewhat. And in fact, Antires has actually built his own testing harness for doing partition tolerance tests. So I'm really happy with how that's progressed. Okay,
so Antires, for those who don't know, is the author, Salvatore Sanfilippo of Redis, right? Okay, so MongoDB. You talked a bit about it, but maybe give us some more detail about it.
Yeah, MongoDB lost data at every consistency level. The unacknowledged writes, of course, are not safe because you're not checking to see if they actually went anywhere. You're just throwing them out into the void and hoping they arrive. If you write to a single node or 2 nodes, those are also not safe because if that node crashes, it may not have replicated its data to the remaining nodes in the cluster. And so a new node, a new leader can come up without knowledge of those writes and then overwrite your original writes. You have to write with write concern majority, and that also turned out to be broken because it would claim things were successful when they weren't. That bug was since fixed. I believe Tokutech has published additional analysis of the Mongo replication protocol. I think there are actually still bugs in it, but I haven't gone back and looked personally. One of my goals for this next round of Jepsen is to do a second attempt.
Okay. REAC.
REAC lost staggering amounts of data in last write wins mode. This is not a new result. The docs tell you, like, it is not safe to do this. You can only write once in last write wins. Last write wins essentially means any write wins when a partition occurs. However, if you use CRDTs and set addition is a safe operation to do in a CRDT, you recover 100% of all writes and complete availability. So it does behave exactly as you'd expect for an AP system. You just have to make sure to use siblings.
Okay. So the next one is Zookeeper. That's a different kind of system, right? I always wouldn't have categorized it as a database, but clearly it is a data store with a particular purpose, or typically used for a particular purpose, right?
Yeah, Zookeeper typically is used more for configuration and state data. It all has to fit in RAM, so it's not what you would think of as a sort of traditional OLTP database. But it has the advantage that if you use sync commands, it is fully linearizable. And if you don't use sync, you get linearizable, semi-linearizable writes and possibly stale reads. So it's really a terrific system for doing like distributed state machines. That turned out to pass with flying colors. Now again, the fact that I don't find a problem is not evidence that no problems exist.
No obvious problems exist, obviously.
Yeah, it's just that it happened to pass that particular set of tests, and I hammered on it for quite a while and wasn't able to find another problem.
Okay. NeoDB, one I haven't heard of before.
NeoDB, yeah, that came to my attention because one of the founders wrote some really questionable things about the CAP theorem, and the documentation was extremely confused. The approach they took was essentially to block forever and just accrue writes until memory exploded. Obviously, that doesn't work particularly well. It'll be fine so long as your write volume is sufficiently low, but you also stall all your clients. So it's unlikely that your clients are willing to tolerate 10-minute latencies or whatever. They're probably going to give up and fail. So it essentially becomes unavailable completely during partition as opposed to having partial availability. Kafka had a really interesting bug. I was reading the replication design document for, I think, maybe 08. I think it was 080, and they had this new sort of replication design where you had a set of replicas that were kept in sync with each other. They proceeded in lockstep, but if a replica fell behind or was unreachable, it would be ejected from the in-sync replica set. And this is all negotiated through Zookeeper, which is, I think, a great choice for keeping your cluster membership state. The tricky bit is that they allowed the in-sync replica set to shrink below a majority of nodes. So if you were careful with your partitions, it's possible to get the in-sync replica set down to a single node, which will still acknowledge all of the writes that are performed. So the single node's busy saying, like, okay, yep, I'm taking your data, everything's fine. But if that single node then crashes, or if it loses its Zookeeper connection, the cluster will have an election and choose one of the other nodes, which has no knowledge of the writes that were acknowledged only on that single node. And at that point, you've lost data. That new node will take over and overwrite the previous ones.
So to find those kinds of scenarios, did you have to think of that once you noticed there's a single node happily acknowledging that everything is fine? Did you change the tool to actually look for that case and kill that one node as well, or how did you find? How did you provoke those bugs? How do you make them happen?
The Kafka test was the most tricky. I was looking at the algorithm on the wiki and I had this like gut sense that it wasn't right, but I wasn't sure exactly. So I sketched out a bunch of things on a whiteboard, and I thought I found this pattern that would lead to that problem. And so I actually had a chat with, I think Jay Krebs actually that day, and he was like, yeah, that might be plausible, we're not sure, we'll get back to you, we'll talk about it. And so I went and built the test. And because it requires that you shrink the in-sync replica set first to a particular node, you can't just partition stuff randomly anymore. Mm-hmm. It's not like a simple partition would do it. Mm-hmm. You had to have this sort of 1-2 punch of getting it down to a single node or a majority of nodes, and then making sure those lost their connections. So luckily Jepsen has like a place you can hook in an arbitrary failure scheduler, and I was able to write one that caused that particular failure pattern. And indeed it did lose tons of data. So I think I was... if I recall correctly, that got changed. There's now a configuration switch which you can flip that controls whether or not election is possible in that mode.
Mm-hmm. Okay, so the interesting thing that Kafka, not even the Kafka people claim in any way that it's a database, right? But still, you can show the problems occurring in anything that stores data in some kind and is distributed across multiple nodes, right? Anything will exhibit those kinds of problems.
Yeah, I'd still call Kafka a database. It's a log. It's maybe not what you think of as a traditional database, but it still is a data store for sure.
What about Cassandra?
Cassandra had just introduced a new transaction system called lightweight transactions, and I was able to show that it would deadlock hard, which was a delightful result. And even when the deadlock was fixed, it also lost data. So they found two separate bugs in their transaction system, plus a whole bunch of interesting isolation problems and terminology issues in the docs.
Okay. What about RabbitMQ? Now that's not a database, I'll have to insist.
Yeah, it's a queue. Much like Kafka, I still kind of think of them as databases. They're just different shapes. There was a blog post which suggested building a semaphore or mutex on top of RabbitMQ, and I thought, well, that can't be right. And of course, Avralo Videla and we talked about this back channel. He's like, yeah, this is obviously not right either. I wrote the thing. We'll quietly change that. But it was still a good example of here's something some people do, trying to shape one database into another. How can we demonstrate whether or not safety properties hold true?
Okay. And maybe let's just pick, let's go with the last few as well. So we have etcd and Consul.
etcd and Consul are both very similar systems to Zookeeper. They're configuration stores meant for small in-memory data sets that are supposed to be linearizable. And both of them made the same interesting choice. They're based on the Raft protocol, which is, so far, analysis looks to be solid. The difficulty is that their consistent updates and their consistent reads. Consistent reads did not check to make sure that the leader they were talking to was still the leader by the end of the read operation. And so a cluster transition could occur and you could wind up reading stale data.
And the final one on the list is Elasticsearch.
Elasticsearch was a complete disaster. It lost data from network partitions that were intersecting, from network partitions that were not intersecting, from single nodes being isolated. Even a single node reboot could cause data loss. It was a spectacular cavalcade of failures.
Sounds like you had fun breaking that one.
Yeah, but I think the results have been good. A number of these database companies are using Jepsen internally to help instrument their software. And a lot of them have sort of turned around. They're documenting these failure modes. Elasticsearch in particular now has a phenomenal status page which talks about all the sort of data loss issues and their priorities and links to the relevant tickets. I'm really happy with that.
Right. So that is one thing that I found utterly fascinating. It seems that you broke stuff and told people their systems are just bad and completely broken and shouldn't be built that way in the first place. But nobody really kept cursing at you that badly. Everyone, obviously, people took a look at the results and found them to be valid and actually used that to their own advantage. Is that a reasonable assessment of what happened, or was there a lot of anger at you?
Some people are mad. Some people are not, and it has to do with like how politely I approach the database and how closely I work with the maintainers. Again, this is a social problem. Humans are humans. The results, by and large, I think, have been constructive, and that's always been my goal, to help users figure out what systems are safe and how to analyze their own systems, also to help vendors improve their safety. But I'm one person, before I was doing this in my free time on nights and weekends, and these analyses take hundreds of hours per database. When you factor in all the time writing the tooling and researching papers and writing up the results, it's just a lot of work. So I can't be the QA department for the internet, right? Like, ultimately, I had to inspire the companies to care themselves. And then it becomes a competitive advantage for them because they can claim, hey, we're actually safe according to these metrics.
So I think you mentioned that before. There are a lot of papers that people can read. They may not be the most interesting nighttime reading, but there is a lot of research out there for that stuff. So do you feel that some people didn't do their research properly before building a distributed consistency resolution protocol or implementation?
Keep in mind that everybody who is building a database is under tremendous pressure, financially, in terms of time, in terms of staffing. There's a ton of things that have to happen, and it's an incredibly difficult job. So just because people didn't read literature, weren't aware of it, or didn't design something correctly, it's not that they're bad engineers per se. It's just that these problems are sort of poorly understood, and there's not a culture to support their understanding yet.
Mm-hmm.
One of the things I want to do with Jepsen is change engineering culture to be a little bit more aware of failure modes and how to reason about them.
Mm-hmm.
So it depends on which sort of company you talk to, what their engineering culture is like. Basho places a very high value on papers, and it shows in their engineering. While they do have data loss and corruption bugs from time to time, I think their general architecture has proven to be solid. A company like MongoDB, they made some obviously terrible choices as far as safety goes, but they also made those choices because they knew they had to get this database out the door quickly to build traction in the market. So in some cases, it's a deliberate trade-off. We're going to do the less safe thing. People won't notice until later, and by that time, maybe we can fix it.
Okay.
Which is a valid business strategy, I suppose. My principal concern is that people document and explain and communicate their uncertainty or their possible failure modes to users. I don't need people to be 100% safe. I just want them to be honest.
Right. So that is something that I find very interesting. If the different trade-offs, sometimes there are even valid trade-offs, right? As you mentioned, if it's documented and if it's very openly communicated that there are certain restrictions that you have to be aware of, you obviously have to address them in your application layer, right? You have to do something to work with that database. It might be okay to lose some data. Maybe if you're using a search engine, maybe it doesn't matter that much if something that you write to it is lost, right? Depending on what kind of stuff it is that you search for or that you built this index for, right? So what are some of the strategies that you can use in your own application? Or let me phrase it differently. What's a good strategy? I mean, for developers, if they look at all those things, are they supposed to pick the one that got the best results in your testing with Jepsen, or what are the kinds of trade-offs that people have to make, and how do they address them once they've made them with the data store in their application layer? You can make two answers out of that if that was too much of a question to ask.
I really want to avoid making specific endorsements. Because not every database is suitable for all problem classes, right? Typically, you're going to choose several databases that fit your particular needs as far as availability, performance, and distribution go.
Mm-hmm.
And also, just because I didn't find problems doesn't mean there aren't problems. And you also have to consider other factors like ergonomics, availability of tooling, availability of expertise. Can you hire people to run the database? Can you afford the licensing fees? So there's a lot of things you balance in addition to safety. Just because something is theoretically unsafe does not mean you'll be bitten by it.
Mm-hmm.
I've been at several companies now with Elasticsearch and Prod, and every one of them has been a tire fire.
Mm-hmm.
That I would not recommend Elasticsearch at all if you care about having your database cluster or having your search system actually available and responding to requests and having data in it.
Okay.
However,
that doesn't sound like an endorsement.
Oh yeah, it's definitely not. However, it has a phenomenal API. It is probably the most popular of the available tools. There's plenty of library support. People continue to choose it because search systems don't actually have to have all your data.
Mm-hmm.
Now, I've seen it do some interesting things like lose a third to an eighth of the data set from a node reboot, and at that stage it starts to be really problematic for us. But in certain cases, that's still okay, and if you're refilling it, it's fine.
Mm-hmm.
So, this is one of the things where I want people to just think really carefully about what kind of safety they really need, and then you choose the database that will satisfy that level of safety. And in certain cases, you can kind of make a more loose cultural decision, like Zookeeper, etcd, and Console. Zookeeper's API is complicated. The clients are not easy to understand. It has a really complicated connection model, and I mess it up all the time.
Mm-hmm. But Zookeeper and Console, the etcd are excellent tools for just, for the purpose that they're intended for. I would assume they are, right? For the configuration use case. That's a different one than storing
one of those three, right? But even though etcd has, I think, a very nice, simple HTTP API, it has only been around for a couple of years. And so it has not yet hit all of the various interesting production failure modes that Zookeeper has, and it's going to take time to stabilize.
Mm-hmm.
So I think people are finding out with Console and etcd, there's all these surprising behaviors that the developers haven't seen yet, because it's this only happens once you're at this request volume, this cluster size, this sort of latency pattern.
Mm-hmm.
Then you get this weird explosion of memory and then a GC pause or whatever. And Zookeeper, has also seen these things. So maturity is, I think, even though you can be based on a solid theoretical understanding, it takes a while to iron out all the kinks.
So maybe let's talk a bit about how you actually built Jepsen. So because one of the things that I found interesting was your choice of closure for it. Was that just coincidence because you happened to be familiar with that language, or was it a conscious choice to use it for that purpose?
I wrote the first proxy in Erlang, actually, and it didn't go very well. I wound up using a Ruby deployment tool called Salticid that I wrote to do the network automation, like killing nodes and causing network failures. And then I wrote the analysis system in Clojure because it has really nice facilities for working with data, and because pretty much every database has a JVM client somewhere.
Mm-hmm.
So I had access to all the regular Java clients. They're decent quality. They're easy to interop with. And the performance in Clojure is acceptably good. So it was a natural choice for those reasons.
Mm-hmm. Okay, so there was no particular strength of Clojure that you could exploit, except for its general purpose, usefulness.
It's a nice general purpose back-end language, and it's especially good with databases because while it's certainly not as fast as Java, it's certainly a lot more concise, which makes it easier to sort of reason about the correctness of your code and to write complex data analyses in a few lines. The newer versions of Jepsen actually are written in Clojure for good reason. They have certain macros and DSLs and so forth that take much more advantage of Clojure's concurrency primitives, of its syntactic transformations. Those things would be a little trickier to port to a different language, I think.
Okay. Do you know of any comparable work? Are there other tools like Jepsen by vendors or by other researchers?
It's very much a system I built because I needed it, but it only addresses a very particular subproblem. There are quite a few academic network modeling tools, but most of them are aimed at you write your algorithm inside their language and it checks the validity of it. Spin and Promel are both algorithm checking languages. You can write something in like C or a formal language like TLA Plus, and it will check the model to make sure that it satisfies whatever invariance you describe. You can run your entire network in a simulated system that does accurate message passing and stuff. The problem I have is that, of course, I don't control any of these databases. They're just programs that run on Linux or whatever. So I had to have this black box system where I could induce the failures externally and instrument the system externally and hopefully get some useful results out of it. So Jepsen has a sort of funny shape to account for that problem.
Mm-hmm.
I'm not sure. So Antirez Salvatore has written his own partition testing tool for Redis. There are failure tools for measuring Cassandra that are internal. Riak has extensive stuff written in QuickCheck, which is a generative testing tool for Erlang and Haskell and so forth. Yeah, I think most vendors have these sorts of things. Actually, FoundationDB has quite impressed me. They have not only extensive software simulation of their message passing system to verify its safety, but also they have dedicated hardware that can have induced failures. They can actually have a robot flip a switch on the switch or whatever and turn it off and see what happens.
Wow. Okay. So can you elaborate a bit on how Jepsen works internally?
Yeah, so Jepsen has gone through a few iterations. I mentioned the sort of set addition problem earlier, where you add numbers to a set in the database and read it back. But I've wanted to test more strong consistency classes, like linearizability. And for that, I can't just do unordered operations like a set. I need to have more complex data types, like a lock, or an integer with compare and set operations, or maybe even an SQL table. I'd like to be able to model these complicated things and verify their correctness. So I've written a tool called Knossos, which does model checking against a history. It will evaluate whether a model, like a register, or a set, or a queue, whether that model is consistent with the operations we observe from a database. And then Jepsen is responsible for building a bunch of random operations, like set the register's number to 2 if and only if it's currently 3, or add the number 3 to the queue, dequeue something. And then it has clients which will apply those operations to the system. So the combination of the randomly generated operations, the history of how those operations played out in the system, what the different clients actually saw the database do, and then the model checker verifying that history is consistent with what we think the system should do, those three give you a measure of safety.
It reminds me a bit of the approach taken by things like QuickCheck, Is that the same?
Exactly.
Okay.
Yeah, it's very much inspired by QuickCheck, where you have a model that describes what the system should do in simple, concrete terms. Okay, if I add a number to a register, the new value of the register should be that number plus the old value. Or if I add an element to the set, it should be one bigger, and if I do a read, I should see that number.
Okay.
You write down simple laws about the system, and then generate a bunch of random instructions, execute them, and see what happens.
I'd go back to some theory, if that's okay with you. There has been a whole lot of research into algorithms for resolving for finding a strategy to resolve the consistency problems that arise. Are there some basic ones that people should know, or that you would like to point people to?
The gold standard is Paxos. If you don't know what you need, choose linearizability. It's going to be the safest of all your options.
Can you explain what Paxos does? How does the algorithm work? If that's explainable in a podcast, briefly.
Honestly, Paxos is a subtle and dark magic, which I'm not qualified to explain verbally. I need a whiteboard, and even then, it's a little dodgy for me. The end result is that Paxos gives you a system of participating nodes in a cluster which can come to agreements on certain decisions. In practice, you can translate that consensus algorithm into other things like a replicated state machine or a log. There's another protocol which is much simpler called Raft, which is, as far as we know, equivalent to Paxos. And there's also Zab, which is the Zookeeper Atomic Broadcast paper, and there's Zab as actually implemented inside of Zookeeper, which are slightly different things. All of those also offer linearizability.
So as a lowly application developer, I don't actually have to implement them, because I use some tool that has implemented those things correctly. Do I have to know how they work? Do I have to know the consequences of using them? Because I have to have some insight into what it is that I'm using there, right?
Ideally, you don't need to understand how they work. All you need to know is what classes of history do they allow. In a linearizable system, you're guaranteed once your operation completes, it's going to be visible. Every operation will appear to take place between the time that you send the message, starting it, and when you get back the result saying, hey, it's done. Now, there are other algorithms. If you have sequential consistency, you no longer get that real-time guarantee. Your message could come back saying, hey, it's done, but it could logically take effect later. Or in the case of read committed, you can get certain read anomalies where, okay, I read committed data, but it might be possible for me to still see a phantom for a predicate not to be consistent with the current state.
One acronym you mentioned a number of times was CRDT. Can you give us a brief introduction into that concept? What does it stand for, and what does it mean?
So CRDT is a convergent replicated data type. We all use data types, right? Like sets or strings or arrays. A replicated data type is one that can exist in multiple places. So you could have a copy on one computer and a copy on another. And if it's convergent, we want to guarantee that if those copies communicate, they will come together into some final value that we can agree on. So this is really useful for AP systems where you might update a counter on two different nodes that don't communicate with each other. And then later they exchange information and come into a new counter value, which should include both counter increments.
So, taking that example, how would that be implemented? Do you use some version tracking or timestamps, or is that the internal implementation of that particular CRDT then?
The really nice thing about CRDTs is that if you implement them, if you follow these simple rules, you basically get safe convergence for free. Everything else becomes a performance optimization. So the rules you have to do to be a CRDT are to be associative, commutative, and idempotent. Associativity means that I should be able to change the parentheses around the function application, f of a and b, and then applying that to f of that and c. That should be equivalent to switching the nesting order. Commutativity means that it's argument order independent. So f of a and b is equal to f of b and a. So those two things mean that I can apply the operations in any order on any replicas to get the same results. The last one, idempotence, means that if I apply the same operation multiple times, it only takes effect once. And that's critical because it means I don't have to only send a message to my peers once. I could keep sending them my update over and over and over again, and it will have the same safety properties.
Mm-hmm.
So the convergence strategy for CRDT, once you follow those rules for your merge function, is you just spew copies of yourself at everybody else, and they spew copies back at you, and you just call the merge function to combine them, and you're guaranteed to come up with the same answer.
So are there then standard implementations of CRDTs of various kinds and standard libraries that people can use, or is that just something for database vendors to make use of?
I think it's most efficient if the database vendor does it. So there are CRDTs built into Riak, and there's something kind of like CRDTs in Cassandra. I think some of the SQL data types are and some aren't. Things like sets in, I think, Redis cluster might end up looking somewhat like CRDTs at some point.
Mm-hmm.
And you can certainly implement your own on top of a database. So in Riak, all data types should be CRDTs unless you're using the strong consistency buckets. In Cassandra, all of your data types should be CRDTs. And you can implement that logic just by having your own merge function in your code. So you read a value, merge, and then write back.
Okay.
There are some common ones. In RIA papers describing CRDTs, and also what's the second paper? Anyway, if you Google for CRDT papers, Chris Micklejohn has a bunch of these, and they describe a few common implementations. You can build last write wins registers. You can build sets that grow only, sets you can add to and then remove from once, sets where you can observe anything you've already removed. You can build lists if you have an ordering relation. You can get maps of certain types of maps. It's a little bit tricky because in order for them to be convergent, you have to give up on certain properties about visibilities. So your counters, for example, maybe all of your inserts to a counter are going to be saved and eventually seen, but you don't know when they'll be seen. And maybe the space guarantees are different. So in a counter, you have to have a slot for each and every actor in the system for a typical row-only counter. Mm-hmm. For an observe remove set, you have to carry with you a tag that identifies all the inserts and all the deletions. So the space complexity requirements are typically worse than a linearizable systems would be.
So we've covered a lot of ground. We've talked a lot about theory, and we've talked about a lot of actual systems. So maybe first of all, is it a reasonable approach for a software engineer to just pick one solution and stick with it, or maybe two if they have different needs? And can they use your post as a guideline as to assess the qualities of the systems?
I think the post will be useful in figuring out how to think about a system. I don't think you can use them as like, oh, buy this database. Ultimately, and I try to stress this in each post and in every talk, it's up to you to measure your system's correctness and to figure out if the invariants you need are provided by the database. So you can read Jepsen posts to figure out, okay, can I get the system to be linearizable or not? But those may be out of date, right? I can't keep updating things all the time. And you might discover that there are certain requirements that I just haven't talked about, which you need from your database. So ultimately, I want to give people the tooling in Jepsen and push the vendors to provide tooling as well so that you can evaluate these for yourself. I think in more general terms, as a software engineer, you're going to need to combine multiple data stores. So you might have maybe Kafka as a log store and Cassandra for immutable AP storage, and maybe Riak for a CRDT store, and maybe Zookeeper for a linearizable store. And you might be shuffling operations into and out of these different data stores. Maybe there's Postgres, maybe there's some sharded Postgres in there for strong serializable operations over subsets of the data set. I think you'll find that your use cases, once you start getting up to scale, require that you use different data types and different data stores for different data volumes. Mm-hmm. Typically, you'll have really high volume stuff that can't fit in Zookeeper or Postgres, and so you have to start sharding it yourself, or you have to start using an AP data store like Cassandra for your high throughput ingest.
Okay, so what are some good resources, some places people could start if they want to familiarize themselves with this topic more?
I think CMeik, C-M-E-I-K, Micklejohn, he's got a great reading list for distributed systems engineers, and that's where I would go for theory. I've written a blog post on strong consistency models, and Peter Bayless has written much better formal work on the topic of consistency. So those are good resources if you're interested in more theory. If you're interested in a short overview of Jepsen, I think the ACMQ article on network partition frequency might be of use because it tells you sort of here's a bunch of different failure modes that we saw in production systems. It's an overview of the different postmortems that we've seen about network partition failures. And the Jepsen posts themselves kind of show you exemplars of here's how a system can fail. But I think it's best to look at those as case reports and not as sort of generalizable results.
Okay. So, thank you very much for this, for all this information. My head will explode in very few seconds. So, thanks a lot for your time, and happy to have had you on the show.
Thank you very much for having me.
For Software Engineering Radio, this has been Stefan Tilkoff. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can write comments on each episode on the website or write a review on iTunes. Mention or message us on Twitter at SE Radio, or search for the Software Engineering Radio group on LinkedIn, Google+, or Facebook. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Thanks again for your support.